Okay, in this video we're going to talk about electromagnetic induction. And this is a phenomenon that was discovered early in the 19th century by a British physicist by the name of Michael Faraday. And we have basically got Michael Faraday's apparatus, his experimental setup here on this slide. So basically what he had is a battery, and that battery was connected through a switch to a coil of wire. And through the coil of wire there was an iron magnet, an iron magnetic core, and on the other side was another coil which was connected up to an ammeter. Now, obviously there's no reason for there to be any current in this coil right now, but what he noticed is when he closed the switch, the ammeter would briefly move. And when the switch was closed and stayed closed, it went back to zero. But when he opened the switch, the ammeter would move again, this time in the opposite direction. And what he realized is that by closing the switch, he's creating a current in this coil of wire. And that current in a coil of wire, we know, creates a magnetic field. So this magnetic field, when the switch closes, this magnetic field is suddenly created. So there's initially no magnetic field, and then suddenly this magnetic field is created and it expands outwards. And it crosses over this coil of wire here. And he realized that it was only that brief moment when either the closing the switch and the magnetic field is expanding outwards, or opening the switch and the current stops and the magnetic field collapses. So only when the magnetic field was passing back and forth over this coil did the ammeter move. This is called induction. We're inducing a current in a coil of wire by having a changing magnetic field. So whenever you have a changing magnetic field, you can have an induced current in a coil of wire. The key point is that it has to be a changing magnetic field. Now, there is an investigation on the website, which hopefully you've done. You've taken a solenoid and a bar magnet, connected the solenoid up to an ammeter. When the bar magnet's not moving, you didn't notice any current in the ammeter. But when the bar magnet is moved, you get a current. And hopefully there's a few things that you've noticed, which Faraday himself also noticed, is that the direction of the current, so the current, the induced current, depends on the following things. So one, the direction of the magnetic field. So here is a magnetic field and it's pointing in this direction. That creates a current going in one way. If I took the north end of this magnet and pushed it into the solenoid, we would get the opposite current. So the direction of the field. Is one thing. The other thing it depends on is the magnitude of the field. Okay, so a stronger magnet creates a stronger current. The other thing that you notice is that it depends on the direction of the change. So when the south pole is moving in, I get current in one direction. When the south pole is moving out, I get current in the opposite direction. So again, the direction of the change. The other thing that you probably noticed that affects it is the speed of the change. Rather than expressing it in the speed, we can say the time that the change occurs, right? So how long it takes to make that change. And then the last thing, which you probably couldn't really do in class because we have a limited number and type of solenoids, but Faraday noticed, was that it depended on the size of the solenoid. So not just the area, so the physical size of the solenoid, but also the number of coils, so however many turns around. So quite an extensive list of things that affect the amount of current in this solenoid. Faraday realized that he could combine a couple of these together, that they were really just, he basically invented a new quantity, and he called it magnetic flux. And the symbol we use for magnetic flux is the Greek letter phi. And magnetic flux is basically the number of magnetic fields, so the magnitude of the magnetic field passing through a given area. Okay? It's important to remember again that only the perpendicular component of the magnetic field contributes to any of the magnetic flux. Okay, if the magnetic field doesn't actually pass through the area, there's no flux. It has to be perpendicular to it. As a quick example, what we might have is a region where there is a magnetic field directed into the page, and if we had two different areas, two different, say, loops of different sizes, so let's say we had a small circular loop, this area doesn't encompass very much of the magnetic field, but a much larger rectangular loop, this has much more of the magnetic field passing through it. So it depends not only on the size of the magnetic field, but also the area, and that means that there's more magnetic field inside that loop. Now the units for magnetic flux are called Webers. Their symbol is a WB, and that is a Weber. So magnetic flux basically is the amount of magnetic field passing through the area that I'm investigating. Now that Faraday had a quantity that could encompass both the magnitude of the field, the direction of the field, and the area that that field is passing through, he created what we now refer to as Faraday's law. And rather than talking about the induced current, he referred to the induced EMF, right? The electromotive force, right? So the potential difference that is creating that current. And he said it depends on the number of coils in the solenoid and how quickly the magnetic flux is changing. So again, the change in the magnetic flux could be a change in the magnetic field, either in its magnitude or direction, or it could be a change in the area of the loop. So maybe the loop getting bigger or smaller, or probably more common, the loop rotating so that it becomes perpendicular and rotating to a parallel. And when it's parallel to the magnetic field, obviously the flux is zero. And it depends on, again, the rate of that change. So Faraday's law tells us the magnitude of the induced EMF, the electromotive force. Now if you look on the formula sheet, there's a negative sign in front of this formula, and believe it or not, that little negative sign is probably one of the more difficult things that you will learn in Physics 12, and it's something called Lenz's law. We're going to devote basically a whole video to Lenz's law later, but we'll come back to Lenz's law in a future video. For right now, let's actually go through an example of how we would use Faraday's law. So here I have a typical question. I have a loop or a coil which has 50 turns or 50 loops on it, and it's in a magnetic field directed into the page. And we're told that this magnetic field is going to change direction so that it is out of the page. And it will also change in magnitude down to 0.10 teslas. So what is the induced EMF in this loop? So again, the induced EMF will be given by Faraday's law. And in this case, I have 50 turns of wire, and I have a changing magnetic flux. Now what's actually changing here is the magnetic field. So we have a change in B. So remember that a change in any quantity is going to be the final value minus the initial value. In this case, what's actually changing is the magnetic field. So we have a change in the magnetic field and the area itself remains constant. So what we are looking at is the final magnetic field minus the initial magnetic field multiplied by the area. So the final magnetic field, don't forget, it changes direction. So if we set the original direction into the page to be the positive direction, the final magnetic field is out of the page, so we have to put it as the opposite direction, a negative. And then we can subtract the initial magnetic field, and it's positive, but we're subtracting it, so we get it into the page. And then we're going to multiply by the area of our loops, so that's pi times the radius squared. And then we're going to divide by the time that that change occurs over to get our induced EMF of 0.14 volts. So when this change occurs, this loop of wire will have a potential difference or a voltage of 0.14 volts if we measured it with a voltmeter. Okay, there's lots of really good examples in the textbook for Faraday's law. I encourage you to try some of them out. And as always, if you have any questions, make sure you come and ask me in class. And in the next video, we'll spend some more time talking about Faraday's law and what this little negative sign means in terms of Lenz's law.